This is a lesson on static and kinetic friction in the classic Newtonian force analysis unit. To review a little, I had talked about friction forces broadly in a lesson on the concept of force in the free body diagram. And I defined it as a contact force that resists the relative motion between two rough surfaces. And so this direction is important, that it imposes the relative motion between two surfaces, and that there's this misconception that friction is always resistive and opposing, when actually there's counterexamples where it causes the motion and causes the acceleration. So watch out when you're drawing free body diagrams that you have a resistive force in the correct direction, and we'll go through some examples. Regardless of the direction of the acceleration, we can draw the direction of this force. And so again, if it's speeding up or slowing down or no acceleration, we consider the relative motion between the two surfaces. So if two surfaces are at rest with one another and there's no acceleration, we can imagine which direction the frictional force would be if the two surfaces were to slide relative to one another. That deals with the direction. When we look at the magnitude of the friction force, we have to consider two factors. The first is the nature or composition of the two surfaces in contact. For instance, if you have rubber and ice as opposed to rubber and the road, there's two different natures of the composition and two different ways those surfaces are in contact and friction acts with them. The magnitude will change. And also the nature of the motion between the two surfaces. There's two ways that it can have a different nature if it's at rest or if it's moving. And hence that's why we have static friction versus kinetic friction. So let's get into some details about how to calculate the actual magnitude of friction force. When I look at the static friction force, the magnitude will take on whatever value it needs to be in order to keep no motion, but up into a certain value, a maximum value. And notice that's represented in the equation here. It's an inequality. It's not an equal sign, it's an inequality. And that's expressing that it can take on some value below a maximum value all the way up into a maximum value. So it would go like this. If I have a low force applied, I would have a low friction force. If I have a higher force applied, I would have a higher friction force. But up into a max value, max friction force static. That happens at mu s times the normal force. Let's look at these symbols in here, and I mentioned this one is mu. This is Greek small letter mu. It's a lowercase letter, mu, and notice it has a tail out front. I write a little tail. Instead of just writing u, I have a little tail out front. This is what we call the coefficient of static friction. And again, this is a quantity that depends on the composition of the two surfaces. This will usually be given, or you may need to calculate it. And there are charts where if you're looking for a particular relationship, you could go look them up in a chart. And often this is a quantity that's calculated in labs. This coefficient of static friction is unitless. It's a coefficient. So by nature, a coefficient is unitless. And it also takes on the value between 0 and 1. So if there's no coefficient of friction, then there's no frictional force, and you would have essentially ice on ice. They would slide without friction. If you have a large coefficient of static friction, you will have a large frictional force, and it will be harder for those two surfaces to move through across one another. The other term in here is the normal force. And the normal force is the force that arises because of the contact between those two surfaces. If those two surfaces were not in contact with one another, there would be no normal force and there would be no friction. That makes sense. They're not in contact. So the more those two surfaces are in contact with one another and the harder they get pushed together, the larger that normal force will be, and therefore the larger the friction force will be. And you will need to calculate the normal force through a force analysis. Sometimes I see people get into a knee-jerk misconception that the normal force is always equal to the weight, and you will miss valuable points on exams for that misconception. We will cover situations in two-dimensional analysis where the friction force and the normal force is less or more than the weight. And so watch out for that. Make sure you're doing your analysis in the y direction or whichever direction you need to really identify the normal force. The kinetic friction force occurs when the two surfaces are moving relative to one another. That's hence the word kinetic. When I look at this equation, it is an exact value. There is an equality here as opposed to the inequality for the previous one. Again, there's a coefficient of friction in here, and this is the kinetic. It depends on the composition of the two surfaces and will always be between 0 and 1. The normal force is also in here, and the same addendums apply, the details to pay attention to in a force analysis in order to calculate this force accurately. And what I'm going to note overall when you solve problems or are given information, that the kinetic coefficient of friction is smaller than the static. And this represents the idea that it is more difficult to get two surfaces moving to one another as opposed to keeping them moving. So again, this is the moving. It's easier to keep it moving than if it's stationary, static. This force will be larger when it's static and smaller when it's moving. As a review, be sure to follow the four-step force analysis strategy, especially if you're having trouble knowing where to start and what equations to set up. Make sure there's a general sketch of the situation. Draw your free body diagram by identifying all your forces and doing a coordinate system and decomposing forces if you need to. Apply Newton's second law. Once you get that free body diagram drawn, you can use it in order to set up your equations in Newton's second law. Then you can identify knowns and unknowns and solve as you need to. Be sure also to reflect on your answer. Does your answer make sense in the context of the problem? And make any notes about what worked or didn't work in your problem-solving strategy. For this, we're going to return to the moving a trunk problem that I introduced on a previous lesson, where we were given a friction, we solved for a friction force, but we didn't know the details of it. Well, in this example, let's explore the details of the friction force a little bit more in depth. And what I'm going to do is get a general sketch going. This is the sort of general sketch that we had going, is that there's two children. One is pulling on a trunk with a force F1, and the other is pushing on the trunk with another F2. And those could be given values, or they could be things that we need to solve for. Okay. In this situation, we also need to get a friction force going. We noted that before there was a friction force going, and we can have that in the free body diagram. More information in this problem says the coefficient of static friction between the trunk and the floor is mu s, that's 0.34, and the coefficient of kinetic friction is unknown. So mu k equals a big question mark. And remember that this is static, so that's when the trunk isn't moving, and this is kinetic, so this is when it is moving. So we'll have to use those appropriately. The mass is given as 90 kilograms. I can write that down as well. Okay. One child pulls on one end of the trunk with a force of 86 newtons. So I can write that down, 86 newtons. What is the force the second child must push on the other end in order to get the trunk moving? Okay, so for me, that's a critical situation, right? Words mean things. And what does that mean? In order to get the trunk moving. So when it gets moving, we go from a situation of zero acceleration to non-zero acceleration. And the trick is that to think about this fact about the friction force is that, remember on the previous slide, the static friction force will increase into a maximum value as represented by the inequality up here, right? it will increase, and then when it just gets moving, we've reached this maximum static friction value. And because this is a critical point in the static realm, we will note that for this part, we will let the acceleration be approximately equal to 0. And you may say, like, it's moving, but it's just barely moving, and it's just barely not moving. It's that exact instance that we have to pinpoint, and we'll say it's still approximately 0 there, and we're going to note that the maximum static friction force is going to be relevant. And so we can put an equal sign in here, mu s times the normal force. We've reached the maximum value, so we can use an equal sign. Okay, so that's setting up some concepts with the problem and applying the idea of static friction as opposed to kinetic. We still haven't drawn the free body diagram, so let's get that in here. I'll do that over to this side. There's F1, which is a given value. F2, we don't know. There's the friction force. There's also forces in the vertical direction. We're going to have the normal force upward and the weight downward. Both of those forces are acting. I'm going to note, because I have a friction force, I'm going to need to know the normal force, so I will do a force analysis in the y direction in order to identify the value of the normal force. And I'll do that over here. I'll apply Newton's second law in the y direction. That has to equal MAY. In the y direction, and I didn't assign a coordinate system, so I'll do that right now. I'm going to assign like this. Up is positive and to the left is positive. So when I write this equation in the y direction, I'm going to note that there's no motion in the y direction, so AY equals 0. Over on this side goes the forces in the y direction with their correct signs. So I would have the normal force as a positive value, and the weight downward gets a negative sign. And that tells us the relationship for the solving for the normal force. The normal force is equal to the weight in magnitude, which is mg. And I can easily calculate that. I'm given m, and I know g, and I can calculate it. Okay, so in order to solve A, let's see what A is asking. What is the force the second child must push? So we're solving for F2 in part A. What is F2? And I feel like I'm ready to set up the Newton's second law equation in the x direction in order to figure out that horizontal force, right? The F2 is horizontal, and so I'll do a force analysis in the horizontal direction in order to isolate it. The acceleration in the x direction, we've noted, is 0. The forces on the free body diagram, remember what goes on this side is all the forces on the free body diagram in the x direction. When I look at that, I have F1 plus F2. Those are both in the positive direction, and the force of friction is in the negative direction. And this gives me the equation to be able to solve for whatever I want to be able to solve for. So when I look at my knowns and unknowns, I know F1, and I know how to calculate the friction force, and I'm asked for F2. So let's solve this equation for F2. F2 will equal the force of friction minus F1. I know the force of friction. The force of friction is mu s times the normal force, and the normal force is equal to mg. So I'm just going to put mu s mg minus F1. I know all the values for these, so I get 0.34. I'm going to move it down here. 0.34 times 90 times 9.8 minus F1. F1 is 86 newtons. So when I solve for F2, when I run this through the calculator, I get 213.88 newtons. Or you could say about 214 newtons. So in order to get, if the first child's pulling with 86 newtons, in order to just overcome that maximum static frictional force, the other child has to push with 214 newtons. So we answered that question. Part B says one child pulls on one end of the trunk with a force of 86 newtons, while the second child pushes on the other end with 136 newtons. So in this situation, they give me F2. They've changed it, and they give me F2. F2 equals 136 newtons, and F1 is still 86 newtons. Okay. This causes the trunk to move at a constant speed. Okay, I know what that means. At constant speed, I know the acceleration equals 0, and it's moving so that I have a kinetic friction going on. The kinetic friction is the moving friction, and that'll be the coefficient of kinetic friction times the normal force. I'm going to remember from the beginning of the problem, it says that the coefficient of kinetic friction isn't given, it's unknown, and we're asked to determine it for this part of the problem, determine the coefficient of kinetic friction. So we're going to have to solve for this value. Okay. So I already know my relationship for the normal force. Nothing's changed in the problem other than it looks like it's moving, and this child, we know how big that force is from that second child. So I'm going to set up Newton's second law again, very similarly to how I did in the first part of the problem. The sum of forces in the x direction equals max. I know mathematically acceleration is equal to 0. That was given. Over on this side of the problem, I'm going to have the same forces, but the friction force is going to be kinetic rather than static like I had over on this side of the problem. We're asked to find mu k, which is buried in here. I'm going to write this. I'm going to move it over to the other side. You get F1 plus F2 equals the force of friction kinetic. And I know that's equal to mu k times mg. So when I solve for mu k equals F1 plus F2 divided by mg. I can plug in values. 86 plus 136, both F1 and F2 were given. The mass is 90, and gravity, I know the value of is 9.8. So when this is solved, I get mu k. When you plug this through the calculator, you get 222 divided by 882, which is 0.2517. I'm going to note that this is dimensionless. I have a value of a force over a force, so newtons cancel on top and bottom, and this is dimensionless, so that makes sense to me. Also, the value lies within the range I expect. Remember, the coefficient of friction, whether it's static or kinetic, is between 0 and 1, and I have it at a little bit more than a quarter. And so you can see, make sure you're drawing free body diagrams. Make sure you're doing an analysis in the y direction to solve for that normal force. Don't get that normal force wrong. Make sure you're solving for the normal force. Once you get that normal force, you can use it in order to calculate your friction forces. Apply Newton's second law once you get all your forces sorted out, and then you can say, what do I know and what do I don't know, and solve algebraically for the quantity you're looking for.